In Chapter 13, we will be looking at unsaturated hydrocarbons. So these are hydrocarbons that may have a double bond or a triple bond. And one of these hydrocarbons can be used to make vinyl chloride. Vinyl chloride is an alkene that is used to make polyvinyl chloride. And that's a polymer that can be used in blood bags, tubing, and other materials that are used for hemodialysis. An alkene is a hydrocarbon that has one or more carbon-carbon double bonds. And in these double bonds, there's no carbon-carbon rotation. The formula for these is similar to the cyclic alkane, so there's CnH2n for that. And this carbon-carbon double bond functional group is an alkene. An example of one would be ethylene. So you can draw it like that. It looks like the equal sign. Sometimes it helps to draw the hydrogen in. This is ethylene. Or it can also be called ethene. And these have that ene ending because there's the alkene there. Each carbon is trigonal planar. The bond angle is 120 degrees. When we're dealing with alkynes, these are hydrocarbons with one or more carbon-carbon triple bond. So the formula here is CnH2n minus 2. So this here is an alkyne. An example of the simplest one is acetylene. That's the common name. Which could be confusing, I suppose, because it has that ene ending. The IUPAC name for this is ethyne. So it has that F beginning and then the ine ending for alkyne. Each of these bonds is linear, or the shape is linear, and the bond angle is 180 degrees. As a banana ripens, it gives off ethylene, and if you have a tomato sitting next to it, that ethylene can also speed up the ripening of a tomato because that is a plant growth hormone. When we look at physical properties of alkenes and alkynes, these are nonpolar compounds because it's just carbon and hydrogen bonds. They tend to be insoluble in water. They have low melting and boiling points. The unsaturated hydrocarbons have less than the maximum number of H atoms possible. So in an alkane, as an aside here, an alkane is saturated. Every carbon in that molecule has the most number of hydrogens that it can have. But in an unsaturated hydrocarbon, it has less than that maximum. So on this carbon here that's in red, that carbon has a CH3 bonded to it and one hydrogen. So it's unsaturated because of that double bond. If we're drawing the skeletal structure of this, we have the double bond and then a methyl group coming off of there. So there's a single bond here on one side and then a double bond on the other. So we keep the double bond when we draw the skeletal structure. If we're drawing the ethyne, these are single bonds here. And to draw the skeletal structure of an alkyne, you have the 2 points there of the triple bond, and then we just draw a bond to the carbon. So here we're going to draw a complete structure for each alkene or alkyne. I can count the number of carbons. I have 4, so this would be 1, 2, 3, 4. My double bond is between 1 and 2. And then for the alkyne, I do these a little bit different so I know where my bond angles are at. So if I start with the triple bond that's 2 and 3, I know that it has to be linear out from there. So this is 1, that is 4, and then 5. That's how I would draw those two. The next problem here is to complete the structure of zingiberine. It's a component of ginger root. So we want to draw all the hydrogens in that are missing and then draw the skeletal structure for that. And ginger, if you did not know, is used as a spice in Indian and Asian cooking. And ginger candy is sometimes used to treat nausea resulting from seasickness or even morning sickness. Okay, so what I'm doing here is I'm just going through, and wherever I have carbon, I'm going to draw in as many hydrogens as it can hold. So this carbon right here that I'm going to put a star next to, that carbon is making 2 bonds to the carbon above it, another bond to carbon, and another bond to carbon. So that one actually will not get any hydrogens. This will get 1, 1. All right, so there's all the hydrogens, and to draw the skeletal structure, I have a 6-membered ring. There's a double bond here, here, a CH3. So that's what that one looks like. When we're naming alkenes and alkynes, we need to find the longest carbon chain that has both carbon atoms of a double bond or triple bond. If you have a double bond, it ends in -ene. And if you have a triple bond, it ends in -ine. Then we're going to number the carbon chain from the end that gives the multiple bond lower number and name substituents, and then write the name. So for this first alkene, the double bond is included here in the longest carbon chain. The alkene is going to get the lowest number, so that's going to be 1, 2 where it starts. I have a methyl group at 3, so this becomes 3-methyl, 1-butene. And if you leave off the 1 there because it's the first one, then that's just implied, and that's okay too. For this alkyne, I don't want to number it left to right, because if I number it that way, my alkyne will be having a lower number, so I'm going to number it this way. And remember that on each side of those triple bonds is 1 carbon, so this will be 4-ethyl, 2-hexyne. So the 2 is where the triple bond starts. 6 is hexyne. Hexyne is for the number of carbons there. Dienes have 2 double bonds, and the name ends in a diene. So this one has 2 double bonds at 3. There's 4 carbons total, so this will be 1,3-butadiene. So but is for 4. A diene tells us that there are 2 double bonds, the diene, and the 1 and the 3 tells us where they both start. If I number this way on the second molecule, this will give me where the lowest alkene start place. So this will be 5-methyl, 1,4-hexadiene. So again, the 1 and the 4 tells us where the carbon-carbon double bonds start. For cycloalkenes, our carbon-carbon double bond usually starts at 1. So to give this first one the lowest numbering, I would use this as 1 and this as 2. If I had started the numbering at the top, then my substituent would be at 2, and this way it will be at 1. So this will be 1-methyl cyclopentene. And on the second one, our substituent should not be at 1, but our double bond should be. And I'm going to number this way to give it the lower numbering. So this is 3-methyl cycloheptene. And this is kind of a weird one where our 1 is going to be at the methyl, but then we're going to number around. And your double bond has to be between 1 and 2. So this is 1,6-dimethyl cyclohexene. Sometimes alkenes will have common names. So we saw ethylene earlier, which is just CH2CH2. And acetylene is the same as ethine. This is the same as ethene. So we've got a couple of practice problems. I'm going to give my alkyne the lowest numbering. I have 5 carbons total. This is 3-methyl pentyne. The alkyne starts at 1, so I don't have to put a number there. Okay, so this one's got 2 methyl groups at 3 and 4. My double bonds start at 2 and 4, so this will be 3,4-dimethyl 2,4-heptadiene. Our lowest numbering here will be 3-ethyl cyclopentene. As we introduce double bonds into structures, this can create different constitutional isomers. And remember, a constitutional isomer has the same formula, but different connectivity. So one constitutional isomer for butene, or C4H8, has a double bond between carbon 1 and 2. I can have it between 2 and 3, or I can have a 3-carbon chain with a branch and have the double bond there. So if I look at this compound right here with a double bond, there's different stereoisomers we can have. So they're connected the same, but the 3D space is a little bit different. So this is 2-butene. If I draw a line over the double bond, the large groups here are on the same side of that red line, so they're both on the top. That makes this cis-2-butene. So this is the cis isomer. So cis meaning same side. I can also have them on the opposite sides, which you can see on the other end there, where my groups, if I draw my red line across here, one is on the top side, one is on the bottom side. This is trans-2-butene. Okay, so these are different compounds. The cis and trans are different compounds. They have different names, so they are different compounds, and they will behave differently, but they are stereoisomers of each other. So in a stereoisomer, the connectivity is the same. So same formula, same connectivity. It's different 3D spatial arrangement. So the cis-2-butene and the trans-2-butene are still 2-butene. So that double bond is still occurring between 2 and 3. But in the cis, those 2 methyl groups are on the same side as each other. And in the trans, they're on opposite sides of each other. So we can look to see how stereoisomers are determined. In this alkene here, we have groups A and B and C and D. In order to have a stereoisomer, A and B have to be different from each other. And C and D also must be different. If I look at the 1-butene, on the double bond, there are 2 H's here. These H's are the same, so we can't have cis-trans. So if those 2 groups are identical, then you can't have cis or trans. Even though on the other side, these are different. So the H versus the ethyl group, those are different. But if one side is the same, then we can't have cis-trans possible. So our problem below here is to draw cis and trans 3-hexene. So 3-hexene has 6 carbons, and then the double bond starts at 3. So I've drawn one already just from the zigzag. And to determine which one this one is, I'm going to draw my line over the double bond. and look at each of the carbons. So at carbon 3, I have a CH2CH3, and then there's a hydrogen on the bottom. The CH2CH3 group is larger, so I'm going to circle that one. And on the other side, I have a hydrogen versus CH2CH3. This is on the opposite side of the top one. So if you put your finger over that double bond, one is on top, one's bottom. So this is the trans. And there's a little bit of effort involved in drawing the cis. I start with my double bond when I draw the cis. Put my groups down here on the same side. This is the cis. And if you wanted to go through and determine this one, you can draw your line. I have H versus ethyl. This is the larger group. H versus the ethyl. This is the larger group. Those are on the same side, so that one is cis. Bombacol is secreted from the female silkworm moth in order to attract mates. And this contains 2 double bonds. Each of them have 3-dimensional arrangements that are different, and it's required for it to be biologically active. So we're going to determine if those double bonds are cis or trans. So I'm going to look at the first one here. My large groups are here and here. Those are on the opposite sides, so this first one is trans. And then if I look at the second one, here's my double bond line. My large group is here and here. Those squares are on the same side of that red line, so this is a cis. So pheromones such as this one of the structure that we see here, this bombacol, these have been used to control insect populations. In some methods, they put the pheromone in a trap that has a sticky poison or substance, and the males are then lured into the trap by this pheromone. Otherwise, the pheromones can be released into infested areas, which confuses males who then cannot find the females. Okay, so we can define our stereoisomers now that we've identified a few of them. These are isomers that have a different 3D arrangement of atoms. So if we look at 1-butene and cis-2-butene, these two are constitutional isomers of each other because they're connected differently. The double bond's a different location. But between cis-2-butene and trans-2-butene, these are stereoisomers. They both have that double bond between 2 and 3. And then 1-butene to trans-2-butene, these are constitutional isomers. If we look at these to label whether they are stereoisomers or constitutional isomers, we're going to look at A and B. And one of the things you can do is just number the chain to see where groups are at. And A has a double bond starting at 3, whereas B has it starting at 2. So these are constitutional. And then we're looking at A and C. They both have the double bond starting at 3, so these are stereoisomers. In C, my big groups are on the same side, so this one happens to be the cis. These are on opposite sides, so this is the trans. Here we're going to label again as constitutional or as stereoisomers, and then determine if it's cis, trans, or neither. In the first example, I can see right away that they're connected differently. The second one here is just a straight chain, so these are constitutional. And in this example down here, I have 1, 2, 3. These are stereoisomers. Now I'm going to go back to each alkene and see if it's cis, trans, or neither. I can draw my line here. And if it helps, you can kind of cut this in half here as well to evaluate each carbon. So this carbon has CH3s. If they're the same, you can't have a cis or trans. So this is a neither. So I cut that in half. Here's my big group. Here's a big group. And then we're looking on the sides there. They're on opposite. So this is trans. Big group here, big group here. Look at my line, they're on opposites. This is trans. And then I draw my line. This is the circle. My circles are on the same side. This one is cis. If we're looking at saturated and unsaturated fatty acids in different products, the animal fats and vegetable oils are made from fatty acids. Fatty acids are carboxylic acids with long carbon chains. So they have between 12 and 20 carbons in a chain. These are insoluble in water. And a saturated fatty acid has no carbon-carbon double bonds in the chain. And the unsaturated have one or more carbon-carbon double bonds. Naturally occurring fatty acids tend to be cis. Linolenic and linoleic acids are essential fatty acids. That means that they can't be synthesized in your bodies, so they have to be obtained from the diet. And a common source of these essential fatty acids is actually in whole milk. So babies that are fed a diet of non-fat milk in their early months do not grow as well because they're not getting enough of the essential fatty acids. Fats tend to come from animals and are solid at room temperature. Oils usually come from plants and are liquids at room temperature. So you can think of vegetable oil, that's going to be a liquid at room temperature, whereas butter, which comes from animal products, is solid at room temperature. The more cis double bonds a compound has or a fatty acid has, the lower the melting point is. And because cis double bonds create kinks, so they can't pack together and they don't have as much interactions. Lycopene is the red pigment in tomatoes and watermelon. It's also an antioxidant. It happens to have 13 carbon-carbon double bonds. We can also find lycopene in ketchup, tomato sauce, tomato products, and tomato paste. So aside from tomato products, diets that have a high intake of antioxidants that include lycopene or similar have been shown to decrease the risk of heart disease and different forms of cancer. Unlike other antioxidants that can be destroyed when fresh fruits or vegetables are processed, tomato products stay high in lycopene. So tamoxifen is an anti-cancer drug. It binds to estrogen receptors and are estrogen dependent. These also have multiple double bonds, so these are some interesting alkenes.